problems facing the Rutherford model of the atom had their source in the demands imposed by classical electromagnetic theory. Classical electromagnetic theory predicts that an orbiting electron should emit radiation. It predicts that this radiation will change in frequency as the electron loses energy. Eventually, the electron will spiral into the nucleus, causing who knows what to happen. But we can see with our own eyes this prediction is false. Some atoms glow in the dark by emitting visible radiation, but they do not change color, which would indicate a frequency shift, nor do they blow up, disappear, or otherwise self-destruct. It would seem that in its attempts to describe the atomic structure, classical theory delivers us to a frontier. Beyond this frontier, the laws describing some things must be radically different from those envisaged by Newton. Working under Rutherford was a brilliant young theorist, Niels Bohr, who came to the rescue of Rutherford's atomic model. He suggested that the laws governing the motion and behavior of large bodies and particles are inadequate to explain all the motions and behaviors of atoms and electrons. He proposed that an orbiting electron, despite the fact that it is an accelerating charge, does not necessarily radiate energy. A relatively new proposal, put forward by Max Planck, who in the late 19th century had held the Berlin Chair of Theoretical Physics, provided Niels Bohr with his starting point. Planck proposed that matter, when emitting or absorbing radiation, does so not continuously as had been thought, but rather in discrete bundles of energy. Each bundle is called a quantum. Bohr knew that electrons traveling close to the nucleus in small orbits possess less energy than those moving in larger orbits. This is because an electron near the nucleus is attracted more strongly by the nucleus than one that is further away. Energy is required and work must be done on an electron in order to move it from a small orbit to a large orbit. Bohr reasoned that the energy difference between the smaller and larger orbits must somehow be related to Planck's discrete bundles or